So last year I tried to build my own electric motor, more specifically to build my own switched reluctance motor, or SRM. And the goal was to make a motor that was actually good enough to be able to use it for something, right, to power something. And while I did build a motor that actually worked, which was cool, it wasn't anywhere near good enough to actually power a thing. Right? It wasn't very efficient, it wasn't very powerful, it just didn't work all that well. So ever since I made that thing, I've wanted to have another go at this. And so a while back, I started building a new electric motor from scratch, and that's what this video is all about. So the type of electric motor that I want to make is once again a switched reluctance motor, or SRM. And the reason I want to make such a motor is basically because an SRM is kind of an unusual, uncommon type of electric motor that you don't see all that much. And to me that makes it more interesting. I figured if I'm going to make something completely from scratch and put in all this effort, it might as well be something a bit unusual, because that makes it more worthwhile, at least in my mind. So first of all, what is an SRM? Well, if you want to know all the details on how it works, I recommend you watch the video that I made about this type of motor about a year ago, but here's a very quick summary of what it is. So an SRM is basically a brushless type of electric motor that doesn't use any permanent magnets, and it also doesn't use any induction windings on the rotor. So what you have is a rotor that is entirely made out of usually steel or iron. So let's say you have a 6-pole SRM. That might look like this. So you have a 6-pole stator with 6 coils on it, and then inside of that you'll have a 4-pole rotor, which is just basically a pure block of iron that is in this case shaped like a plus sign. And so when you energize a set of coils on opposite sides of this stator, then the iron rotor will align itself with those 2 poles. And then once that's done, you can energize the next set of coils, so the rotor will align itself with those, and you keep going like that, and your rotor is spinning round and you have an electric motor. Also, typically you'll be using an SRM in a closed loop configuration, so the angle of the rotor is being monitored, and the switching is done based on the angle of the rotor. So when the rotor reaches the right angle, then you switch to the next set of coils. So it's the angle of the rotor that dictates when you switch, and it's not the switching that dictates the position of your rotor. This also means that if you have an SRM and it's running, if the load gets heavier, it'll slow down, and if the load gets lighter, it'll speed up, just like a regular DC motor that is running, for example. Okay, so now that we know all that, let's look at what I came up with for my design. So what I have in mind is to make a radial flux machine. So last time it was axial flux, this time I want it to be radial flux, so the rotor is going to be inside of the stator, like in a classic electric motor design. And I want it to be a 12-pole machine, so it's going to have 12 poles on the stator and 8 poles on the rotor. Now, the first challenge was to make a rotor and a stator, and this is not a trivial task because this time I wanted to make them laminated in the same way that professionally built motors are. So if you've ever taken apart a real electric motor before, then you'll have noticed that they're not made of a solid block of steel that they wind the coils on, but instead they are made up of stacked layers of steel instead. And the reason they do this is to deal with something called eddy currents. So in an electric motor you have a lot of changing magnetic fields, and changing magnetic fields will induce electric currents in things that conduct, so also inside the steel that the thing is made of. And those eddy currents are a power loss. They're going to generate heat, and that heat is energy that came from whatever power source you're using to power this motor, so it makes the whole thing less efficient and it's bad and you want to prevent it. And it turns out that if you make the core out of stacked layers of steel, which are glued together, so there is a layer of poorly conducting stuff in between them, like glue or paint, or maybe an oxide layer in some cases. It turns out that that greatly reduces those eddy currents and therefore makes the motor much more efficient. And so essentially any electric motor you buy is made like that. And I wanted to do this too, but the problem is potentially I could need like a few hundred of these sheets, which would be an absolute pain to make by hand, because I don't have some kind of laser cutter to cut these out for me. I'd have to do it by hand, which is kind of an insane task. So I needed to get these made somehow. So my first idea was to contact a business that actually makes custom motor cores. And so I basically just asked them how much it would cost to make my rotor and stator. And that was going to cost more than €1,000, which was a little bit overkill for this project. So that wasn't going to be the solution. So instead I went to a sort of general purpose laser cutting business, and they were able to cut out, I believe, about 180, I can't remember exactly how many I ordered, sheets of 1mm thick for both the rotor and the stator in total, for a couple €100, which is still rather expensive but doable. So now I had a whole bunch of steel sheets that I could then assemble into my stator and rotor. Now it's not as optimal as it would have been to get from the actual business that specialized in motor cores, because first of all these sheets are 1mm thick, which is kind of on the thick side for motor laminations, and also this is just regular steel. Actual motor cores are made out of a special kind of steel, usually referred to as electrical steel. There is also a whole bunch of different variations of electrical steel, but we won't go into that, which is essentially special alloys that are that have better properties for magnetic stuff. In our case, we're just going to have to deal with whatever random kind of steel the laser cutting business has used, so let's hope it works well. So those are the downsides of this solution, but at the very least it should still be better than using a solid block of steel like I did before. So what I did is I just took all these slices and glued them together into a stack. I put 64 on top of each other, so it's a 64mm tall stack, and then I also secured the whole thing together using a couple of threaded bars with nuts on the end. The next step was to make the windings on the stator, which I did it outside of the machine, and then I put the coils in place and glued them in place using super glue. I started off by inserting some crafting paper into the slots on the stator, which is basically to provide some extra insulation between the copper windings and the stator, just in case there is a little bit of damage on the coating, for example. And also when you're installing the coils, it means if there is a layer of stuff between the potentially sharp edges of your steel stator, it's less likely to damage the coating on the copper wire as well. Now, for those of you wondering, I used 0.5mm squared copper wire, insulated copper wire obviously, and I used 16 turns per coil. How did I get that number? Well, basically it's a little bit of an educated guess based on my previous motor that I made. That appears to be an appropriate number of turns for this size and the voltage that I'm using. So once I had all those windings in place, I could then wire them together according to this diagram. Now, here's a very important note. Just in case you're going to be trying to replicate this motor, do not look at the video footage of me connecting the windings together. Follow the diagram, because I changed it around a couple of times, because of course I messed up and I did some things wrong because I wasn't paying attention. The diagram is right, so just make sure to look at the diagram, then you won't get it wrong. Unless I also mess up the diagram, in which case let me know in the comments. I have an actual piece of paper with notes, because there's a lot of stuff that I did. Right, so the next thing I did was I put the shaft into the rotor. So for this I wanted to use an 8mm threaded bar, so I just took the piece of bar and I grinded a flat side on it so that it would fit through the D-shaped hole on my rotor, and I just secured it in place using a couple of nuts. Now this turned out not to be great, as we'll get to later on. Then I made the front and back plate of the motor, which I just cut out of a bit of steel. I drilled some holes in them so that I could mount these to the stator. I also drilled some holes in the center that the shaft is going to go through. And then in the front plate, I drilled some additional holes that could be used for mounting the motor onto something, in case we're actually going to use this. And on the back plate, I drilled some additional holes for the wires to go through. Then I took a bit of tube with a very specific inner diameter of 12 millimeters, which I cut a little piece off, and I welded that to the front and the back plates. This is for holding the bearings later on. Then I cleaned up these parts and gave it a paint job to protect it from the elements, or at least that's what I tell people. It's obviously just because I like the color. And then finally, once that had dried up and it was all nice, I could actually assemble the machine. And so I did, and it kind of fit, but it didn't fit all that well, because it turns out an 8mm threaded bar is not actually suitable to use as an 8mm shaft. It's the tolerance is not good. An 8mm threaded bar is quite a bit smaller than 8mm. If I were a mechanical engineer, I would have known that. So what I did is I took the shaft out again, and I ordered on the internet an actual 8mm shaft, which I then once again grinded a flat side on, hammered it into the rotor, and then we had a new shaft. I then also cut an 8mm thread on both sides of it anyway, so that I would be able to use my original plan of securing it horizontally using a couple of nuts. I also very, very gently sanded it down just a little bit so that the bearings would slide over the shaft more easily when assembling the motor, because it was actually a little bit too tight for my liking. And so now the electric motor is complete, which means we can go into the shed and see if it actually works. So first of all, before we test this motor, I have to point out that that looks like a serious electric motor, right? That looks like the business. I don't care how badly this thing might perform. In my opinion, that looks pretty nice. So even if it doesn't work well, I'm still quite pleased with how it turned out. But anyway, as you can see, we got the motor wired up to this circuit board over here, which is a driver board, because as we discussed earlier on in this video, in order to make one of these motors spin, you need to turn the right set of coils on at the right time. So you need to switch those coils on and off in a particular order and at the correct timing to get this thing to spin. And that's what this does. So it's an electronic switching device, and the output of this is connected to each one of our phases of our motor. And in this case, of course, one phase consists of 4 physical coils inside this motor. And basically this thing can independently energize each one of those phases. And then by switching those phases on and off, again in the right order and at the right time, it'll make the motor spin. But of course, in order to do this, it also needs to know the position or the angle of the rotor. And for this, we use something called a magnetic encoder. So if you look at the back of the motor over there between all the wires, just get the camera to focus on it, there's a little thing that's called the AS5600, which is a tiny little chip that can register the angle of a permanent magnet that you place in front of it. And in this case, that's a little permanent magnet which I've glued onto the shaft of our motor. So that device registers the angle of our motor shaft, and it translates that into a signal which it sends to the controller through this yellow wire right here. And that's basically just an analog signal, so it's just a voltage ranging from 0 to 5 volts, representing an angle from 0 to 360 degrees. Now I've got this setup wired up to a lab power supply over here, which is set to 25 volts with a current limit of 3 amps, just to be safe. That's quite low. So if I just turn this on, there we go. the motor controller is going to power up. And now if I start turning this potentiometer, which is basically my throttle, I should be able to get this motor to spin. So, here we go. And she's running. Very nice. That is the homemade electric motor actually working. Now, I don't know how well you can hear this on camera, but the motor is not running perfectly smoothly. It's shaking a little bit. So I think the rotor is not perfectly balanced. You can also feel it when you hold on to it. You can feel that it shakes a bit. So I think we have to take it apart again and then maybe add some weight to one side of the rotor or remove some weight from the other side. I'm not sure yet. But other than that, it is running fairly smoothly. I've actually been doing some testing with this thing off camera, and I've measured the RPM, and I've got it up to about 2000 RPM, and it can easily go faster than that, but again, it starts shaking a little bit, so 2000's kind of the highest I wanted to go with this for now. But that is already way faster than the previous motor did, so I'm quite pleased with that. And when I balance the rotor, we should be able to go much faster with this thing. We are drawing about 0.4 amps of current from the power supply, which is not very much. Makes sense because there is no load connected to the motor, of course. The torque that it produces, at least at this very low power, seems to be decent, at least judging by this very scientific test of trying to stop it with your fingers. That we're consuming about 1 amp there as I do this. If I turn up the power a bit more, it gets significantly more difficult to stop it. There you go. You can see we're drawing about 2 amps there, and it gets kind of tricky to stop it with my fingers, but I can still do it. So, yeah, there you go. So, of course, this is not a really good test of what the actual torque output of the motor is going to be when it's at full power, but I can tell you that for the relatively low current that we're drawing, it's already doing way better than my previous motor. And also, I've actually been running this thing for a while off camera as well, and even when it's running for a long period of time, it doesn't get warm at all. It stays very, very cool, which again is not very, that's not very exciting. I mean, no electric motor gets warm when it's running unloaded, right? That's not a very spectacular achievement, but it is compared to my previous motor, because that one would get very hot even if it was running completely unloaded. So that is an improvement over the previous version. So the efficiency seems to be a lot better. Now, of course, there's probably a lot of you out there wondering how many Newton meters of torque does this produce, or how much RPM is it able to reach, or how much power does it make, like how many watts, right? And the thing is, I want to know those things too, so I do intend to properly test and measure those things in a future episode. But for now, I still have to make a new driver board to properly drive this motor, because this driver board is actually the one I used on my previous motor as well, and it's not very good. It's got a bunch of problems that need to be solved. And also, of course, I've got to mechanically see if I can balance out that rotor so that it doesn't destroy itself if we try to run it at higher speeds. For now, though, I am quite pleased with this sort of initial test run, because it does already look quite a bit better than what I made before. Right, so as you've been able to see, the motor works quite well, I have to say. It runs quite smoothly, although, of course, I do have to take it apart for a bit and see if I can balance out that rotor a bit better so that it stops shaking so much, because at higher speeds that's probably going to be a bit of an issue, and we don't want the whole thing to start ripping itself apart. And of course, I've still got to make this new driver board so that we can properly test this motor and see how much power it produces and how much torque it has, which is pretty important if we want to use this thing to actually drive something. Anyway, for now, I hope you've enjoyed this video. If you did, then maybe consider clicking the like button or even subscribing to this channel. And of course, thank you very much for watching.